Welcome to a session on losses in optical fiber. When light signal propagates through a fiber, it suffers loss of amplitude and change in shape. The loss of amplitude is called as attenuation and change in shape is known as distortion. Attenuation, let it define individually. The loss of optical power as light travels down a fiber is called as attenuation. So we can define the attenuation in another way. That is, it is the ratio of input optical power Pi into the fiber to the output power, which means power of light coming out at the output end, PO. So we are representing the attenuation in terms of attenuation coefficient as alpha. So alpha here is called as attenuation coefficient equal to 10 divided by L, where L is the length of the optical fiber, into log Pi by P naught to the base 10. So in decibels per kilometers, attenuation, this is the mathematical equation of the attenuation losses. Attenuation is mainly due to absorption, scattering, bending. Let us discuss the absorption losses. Absorption losses are mainly three types: ultraviolet absorption, infrared absorption, and OH minus absorption or ion resonance absorption. First, let us discuss the ultraviolet absorption. All these absorptions leads to the losses in optical fiber. Absorption means absorption of light when it passes through the optical fiber is got absorbed by the material itself, which means core material itself. So that's why there is some loss from input to the output. Output not equal to input. Ultraviolet absorption. Absorption of ultraviolet radiation around 0.14 micrometer results in ionization of valence electrons, which means when ultraviolet radiation of 0.14 micrometer passes through the optical fiber, the glass molecule itself absorbs this radiation and utilize it to ionization of the electrons. So there is some loss. Next one is infrared absorption. Absorption of IR photons by atoms within the glass molecule causes heating. Whenever infrared light is passing through the uh, core material, the glass material itself absorbs some amount of infrared light, and it will get converted into heat energy. So there is some loss of energy. This produces absorption peak at 8 micrometers. 3.2, 3.8, 4.4. So 8 micrometers is the major peak, 3.2, 3.8, 4.4 are the minor peaks. So here you can see at a 3.2. These are the major peaks and these are the minor peaks. So these peaks, this peak is due to OH minus absorption, this peak is due to OH minus absorption. This is due to infrared absorption. This peak is due to infrared absorption, and this is due to ultraviolet absorption. This tail is due to ultraviolet absorption. Now let us discuss the OH minus ions of water trap OH minus absorption. So this is due to OH minus ions of water, which means during the manufacturing process, if any water molecule resides inside the core medium, it causes the formation of OH minus ions inside the core material. So they got tapped inside the core and they absorb 0.95, 1.25, 1.39 micrometer radiation whenever it passes through the optical fiber. So here you see. Here you can see. So 1.39, 1.25, 0.95. So this is the 0.95. This is the 0.95 OH minus absorption, and this is 1.25, and this is the 1.39. 1.39 is the major peak, and 1.25 and 0.95 is the minor peaks of OH minus absorption. Next, let us discuss the scattering losses. The molten glass, when it is converted into the thin fiber under proper tension, creates a submicroscopic variation in density of glass, causes inhomogeneity to be present, and acts as a scattering centers in fiber. This leads to the losses. So, to when we are manufacturing the core material, actually the glass has to be in liquid state. It is molten glass and slowly it is cooled. During that process, we need to form a narrow thin core. So we need to apply some tension. This tension creates some submicroscopic variation in the density of glasses, which means some inhomogeneity in the atoms at some places. At some places, atoms are very high in density. At some places, the atoms are rare. That means rarer, which means less dense. Okay, so this causes submicroscopic variation in the density of the glass. This causes scattering losses. This is also known as Rayleigh's scattering and depends upon the wavelength of the light. Scattering losses are inversely proportional to the fourth power of lambda, which means scattering losses is inversely proportional to lambda to the power of 4. Wavelength below 800 nanometer have high Rayleigh scattering losses, and wavelength above 1700 nm have less losses due to IR absorption. So, as per the equation, you can see Rayleigh's scattering is high for less wavelengths. As lambda value increases, the scattering losses got decreases. You can see, so the scattering losses goes on decreases as wavelength increases. Next type of losses is bending losses. Wavefront travels perpendicular to the direction of the propagation. The part of the mode outside the bend has to travel faster than that of the inside. For example, you take this particular core material. This is the wavefront. This is traveling inside the core, and this part which emerged out is traveling inside the cladding material. Core is a highly dense medium, and cladding is rarer medium compared to core. So whenever the light passes through the core, it has to travel slow when compared to the part of the wavefront inside the cladding. But according to the rules of the Einstein's relativity, in a single wavefront, one part should not travel faster with the another part, or one part should not travel faster than the other part according to relativity by Einstein. So the part which enter into the cladding material got lost in the form of radiation. These losses are called as bending losses. There are two types of bending losses. One is micro bend losses, another one is macro bend losses. Micro bend is a small scale distortion. Here you can see it indicates the pressure on the fiber. If something goes on the fiber, a little bit of pressure, and it leads to micro bending losses. Macro bending is the large scale bend. When a fiber is bent through a large angle, it undergoes a strain. The bending strain will affect the refractive index and critical angle of the fiber in that area and leads to losses. Here you can see the light is going out due to the macro bending distortion. The light pulse transmitted through a fiber are of a given width, amplitude, and interval. These light pulses broaden and spread into a wider time interval because of the different times taken by different rays propagation through the fiber. This phenomenon is known as the distortion or pulse dispersion. It is expressed in units of ns per km. Thanks for watching.